All right, here's our last notes of chapter 8, and we're getting away from graphing now, and we're going to talk about different types of variation. We're going to talk about actually 3 types of variation. Okay, the first one let's talk about is direct variation. Direct variation happens when both both entities or both things are going in the same direction. In other words, when they're both rising or when they're both falling. That is for direct variation. So look at this first thing. When you study more, does your grade go up or down? So as the amount of studying goes up, what happens to your grade? It also goes up. This is a direct variation. Okay, as you study more, your grade goes up. And of course, it could go the other way too. As you study less, then your grade's going to go down. They're going to go in the both the same direction. How about this? When you drive faster, does it take you less time or more time? So as your speed goes up, what happens to your time? Well, you can see that your time is going to go down. As your speed rises, the amount of time it takes you to get to your destination goes down. That is what we call an inverse variation. As one goes up, the other goes down. Whereas one goes down, the other goes up. Okay? So, the relation between 2 changing quantities is called a variation. We talked about that. When 2 quantities change in the same direction, we say that they are directly proportional. That's just another way of saying the same thing. And when 2 quantities change in the opposite direction, we say that they are inversely proportional. So there's an equation that goes with each one of those that you're going to have to know. So if y varies directly as x, or y is directly proportional to x, it means the same thing. And then there's a constant k, such that y is equal to kx. This is called the direct variation equation. And again, k is a constant. So for example, y equals 3x would be a direct variation. It just means that x is being multiplied by 3 every time to get y. So that means that the rate, think of it as a rate, is 3. Kind of like, by the way, a slope, if you think about it. Okay, so let's do an example of this. So the period, the time required to complete one swing of a simple pendulum, varies directly as the square root of its length. If a pendulum 12 feet long has a period of 4 seconds, find the period of a pendulum 3 feet long. So here's what you have to do. The first thing you have to do is you have to come up with an equation, something like this. We're going to use variables that make sense with the problem. So what are we talking about here? We're talking about the period of a movement is relation to its length. So let's use P and L. So what does it say? It says the period of a pendulum varies directly as the square root of its length. Here's what that says. The period varies directly, you need your K, as the square root of its length. That is what it says. Period varies directly, so it means we're going to use this direct variation equation of the square root of its length. So that's the square root of L. So now, once you have your equation, you need to find K. How am I going to find K? Well, if I look at the first phrase of this next sentence, it says if a pendulum 12 feet long Well, a pendulum 12 feet long has a period of 4. So I know the period and I know the length. I can plug those into this equation and I'm going to be able to find K. Okay, so the period is 4 is equal to K times the square root of, it says the pendulum is 12 feet long, so the square root of 12. So let's go back. The period varies directly as the square root of the length. We now know that if it has a period of 4, its length is 12. So I can take this and I can solve this for K. Well, let's simplify it a little bit. K times, this simplifies to 2 root 3. So I would divide both sides by 2 root 3. Hopefully you remember your radicals. So these will cancel and K would be equal to, this will cancel into there twice. So 2 root 3. And I don't think we're going to get the radical out of the basement there. We could, but we're not going to for right now. Okay, so now that I have K, I'm going to plug it in. So now P is equal to 2 over root 3 times the square root of L. So now I have my equation. Now it says find the period. So I'm looking for P if the pendulum is 3 feet long. So P is equal to 2 over root 3 times, it says my pendulum is 3 feet long, so that means L is 3, so times the square root of 3. Well, if I multiply these, what happens? The root 3's cancel, so the period is 2. 2 what? It says, let's see, period of 4 seconds, so it was in units of seconds, so that means it's going to be 2 seconds. So again, and it's going to be the same thing for the other different types of variation. You start off with an equation. You're going to be given information so that you can plug it in to find K. You're going to plug that K back into your equation now that you have it, and then you're going to solve for the unknown. All right. Let's look at inverse variation. Now, inverse variation, you can actually use 2 different equations. Each one of these is going to work. And you can see if you take this one and multiply both sides by x, you're going to get this one. I tend to use this one right here. That's just my choice, but you could use either one. But that is either one of these is the inverse variation proportion equation. And notice it also has a K. So let's go ahead and let's do example 2 here. So xy equals k, that's the one I'm going to use. Boyle's law states that if a temperature stays the same, the pressure of a gas is inversely proportional to the volume. So this is going to help us set up our equation. And again, I'm going to use words or variables that make sense to the problem. So it says the pressure varies inversely as the volume. So that tells me that P times V is equal to K, where P is pressure and V is volume. Okay, so now I have my equation. If a cylinder in a steam engine has a pressure of 960 kilopascals, so that means that my P is 960 when the volume is 1.4. Find the pressure when the volume increases to 2.5. So again, I'm given a pressure and a volume that go together. I'm going to go ahead and plug those in. So 960 times the volume, it says, is 1.4. is equal to K. Let me grab my calculator here, which tells me that K is equal to 960 times 1.4. I get, hopefully, 1,344. So now that I have found K, I'm going to go ahead and I'm going to change my equation to have my K. Okay. Now it says find the pressure, so I'm going to be looking for P when the volume increases to 2.5. So that would be P times 2.5 is equal to 13.44. If I divide both sides by 2.5, I should be able to get my pressure. And it's 1344 divided by 2.5, which is 537.6. Okay, now we have to label it. 537.6, what units is pressure in? Well, you can see that it's kilopascals. So let me also point out to you, by the way, so when the pressure was 960, the volume was 1.4. What happened to the pressure? The volume went up to 2.5. The pressure went down. Does that make sense, knowing that we know it's an inverse variation? Absolutely, because remember that means that the entities go in opposite directions. So the pressure went from 1.4 to 2.5. It went up. I'm sorry, not the pressure. The volume went from 1.4 to 2.5. It went up. So the pressure had to go down, and you can see it did go down. Okay, finally, our last example here. Joint or combined variation. So it just means that you're going to put a bunch of them together. That's all it means. That's why it's called joint variation. We join a bunch of other ones. So let's see, the maximum weight that a circular column can support is directly proportional to the fourth power of its diameter and inversely proportional to the square of its height. Holy mackerel. So we have a direct proportion and an inverse proportion. So here's the way I remember it. If it's direct, it's going to go end up on the top of the fraction. So really what we're going to be using here is the y equals k over x, if you think of it this way, for the inverse. So just remember, if it's direct, it's going to go on the top of the fraction. If it's inverse, it's going to go on the bottom of the fraction. So here we go. The maximum weight that a circular column can support is, so weight is equal to, you can't forget your k. You always need that. Directly proportional to the fourth power of its diameter. So that would be diameter to the fourth power, since that's direct proportion, that goes on the top. And inversely proportional, so this is going to go on the bottom, to the square of its height. So wow, the weight is directly proportional to the diameter of the fourth power and inversely proportional, which means it's going to go on the bottom, to the square of its height. So there's my crazy looking equation. Now again, we have to find k. So we have to be given a situation where we know the weight, the diameter, and the height. Let's see. 2 meter diameter column that is 8 meters high can support 1 ton. So 1 ton is what? Let's change that to 2,000 pounds, because 1 ton equals 2,000 pounds. Let's just go into pounds. So 2,000 pounds is equal to k times the diameter to the fourth. Well, the diameter of this column is 2 to the fourth over the height squared. The height of this column is 8 meters. So if I clean this up, it's going to be 2,000 is equal to 16k over 64. 2,000 is equal to, I can cancel that, and it's k over 4, which means my k is 8,000. So now that I have my k, let me plug it in. So it's going to be W is equal to 4,000 d to the fourth over h squared. So this is now my equation. So let's see what it tells me to do now. Find the weight, so I'm looking for W, that a 1 meter diameter column that is 4 meters high can support. So I'm looking for W. It says the diameter is 1, so that would be 4,000 times 1 to the fourth over, and it says the height of the column is 4. So 4 squared. So if I have a column that's just 1 meter in diameter, so it's smaller, and 4 meters high, how much weight can that support? You can see that in construction, this would be pretty important to be able to figure out. So it's 4,000 over 16. I use my trusty dusty calculator. I get 250. 250 what? What did I look for? I looked for weight. So it's 250 pounds. That was another good reason to change it from tons to pounds, so we didn't have to work with fractions. And that is the end of chapter 8.